Let's go ahead now and balance these equations. Remember, the idea is we want to have the same number for every single element on both sides of the arrow. Basically, this is obeying the law of conservation of matter. What we begin with is what we have to end with. It's just been transformed. Nothing gained, nothing lost. So, I look for something different. Here I have 3 calciums. Here, there's only 1. So, switch the numbers. Now I have 3 calciums on both sides, and because I put this 1 here, I can now see that there are 2 potassiums, and so I need 2 potassiums over on the left side. The next one, 2 chlorines, just 1. So again, we're going to switch. Put a 1 here and a 1 there, and now I have 2 chlorines on both sides. And of course, since I have put a 2 here, I need to have a 2 there as well. Now there are 2 sodium atoms on each side. For 23, I look at the SO4s. Here I have 3 SO4s. Here I only have 1 SO4. I treat this all as one thing. So let's put a 3 there and a 1 there, and now I have 3 SO4s on both sides. When I do that, I immediately notice that, hey, now I have 3 H2s, so I'm going to need 3 H2s on the right as well, and with the 1 in front of the Al2, I am going to need a 2 here, so that on the left side I will have 2 aluminums. Now, for 24, if I look at the PO4s, just as I looked at the SO4s before, I notice that they are the same, 1 on each side. If I look at the FEs, there's 1 on each side. So, really what I need to do is pay attention to the hydrogens. And I note that here I have 3, and here I have 3 more, so that would be 6 hydrogens, which would mean I would need a 3 there to take care of the hydrogens. In doing so, I notice that that's going to mean 3 oxygens, which will match the 3 oxygens I have on this side. And since now everything is matching in terms of hydrogen and oxygen, the rest will just be 1s. And then finally, for the last one, remember, I have to worry about the hydrogens first, in the sense of, if I look at what half of this number is, if it's odd, then I need to put a 2 in front of here. Half of 12 is just 6, so I don't need to worry about that. I just leave it as a 1. 7 carbons on this side means 7 carbons on that side. At the same time, I look at my hydrogens. 12 here means I need a 6 there, so that 6 times 2 gives me 12 hydrogens on this side. And then I always do the oxygen last in these type of equations. Right here I will have 7 times 2, 14 oxygens, plus another 6 oxygens. So 14 and 6 gives me 20. 20 will be 10 times 2. And so that is the idea behind balancing these equations. So that's the first thing we covered. Now, how did I come up with these products? The idea was you were supposed to look at what was on the top of the page and notice the patterns. So let's go up to the top and look at the first 4, for example. In the first 4, we have 2 things that get combined into one thing. This, in fact, has a name that goes with it. It's called direct combination. And basically, for most of our examples, we're going to be looking at 2 things get combined into one. And so, if I look at number 21, I see that I have 2 things that get combined into one. Now, how did I know that this was supposed to work this way? Well, I have to remember that, in fact, a calcium ion would be a +2, and a phosphorus would be a -3, and then I do my crisscross, and that gives me my Ca3P2. For 22, I go to the second group. In the second group, I notice that I have one thing splitting apart, and these, in fact, are called decomposition. And I can look at it going in the other direction, 1 breaking into 2. Now, it can break into more than just 2 things, but for the most part, it breaks into 2. So I look at number 22, and I have taken salt, NaCl, and broken it into sodium and chlorine. Now, how did I know that the chlorine was doubled up? Well, first off, I could see that up above, all the chlorines were written as Cl2. However, I could also remember that chlorine is one of the 7 diatomics. They are the gens: hydrogen, nitrogen, oxygen, and the halogens. Everybody else, when they're by themselves, would be written as a 1. All of the diatomics are written as 2, and for the most part, they're all gases. The third group, the pattern that I see here is I have an element and a compound, and then another compound and an element. But what's actually happened is that the elements that are by themselves have switched places in the compounds. So calcium was by itself, but it replaced the aluminum that was part of the compound. So the end result of this reaction, I now have calcium as part of the compound and aluminum that's by itself. These are called single replacements. And so we can see in 23 that I have aluminum all by itself on this side, replacing the hydrogen to give me just hydrogen all by itself. And then aluminum is now part of the compound. And again, in terms of how I got this compound, aluminum, of course, is a +3 charge. Remember our pattern. SO4 from our ion sheet is a -2 charge, and then doing the crisscross gives us our Al2SO4 3. The next group has compound, 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 compound. So basically, we're doing 2 compounds going to 2 compounds, whereas the group just before it basically went 1 element plus a compound went to a compound and an element. This is 2 to 2. However, just like the previous group, we are switching the first halves of each compound. So K, which was with fluorine here, is now with the bromine at the end of the reaction. Barium, which was with bromine to begin with, is now with the fluorine at the end of the reaction. Well, now we have 2 things switching, and so in fact we call this a double replacement. It's somewhat easy to remember double replacement because it's the only one that goes from 2 compounds to 2 compounds. And so we see with 24 nothing but compounds for that particular group. And then finally we have our last group, And in some respects, this is the easiest group because in terms of predicting what the products should be, they all end in CO2 and H2O. In fact, they all have O2, oxygen to burn our fuel, and then produce carbon dioxide and water. And these are called combustion reactions. Now, I mentioned earlier that we have to pay attention when we're balancing combustion reactions to what's going on with the hydrogens. And for example, if we look at the last one, number 20 there, and we note that half of 6 is 3, if we put a 1 right here in front of this, that would mean we would need a 3 here in front of the H2 so that they would both have 6 hydrogens. The problem, of course, is putting an odd number here would mean I'd have an odd number of oxygens. A 3 would mean 3 oxygens right here. Well, over on the left, this is O2. O2 can never be an odd number because no matter what I put there, I'm going to double it, so it's going to be even. And so it's because of that concern that when I look at the hydrogens and I say, hey, if it's cut in half and it's odd, put a 2 there first before you then do the carbons. That is why. That will make sure that the oxygens over here remain even. And so by putting a 2 here, I see 2 times 6, that's 12. So I need a 12 there. Now I look at my hydrogens, 2 times 6, that's also 12. So I need a 6 there to make 6 times 2, 12 hydrogens on this side. But that's now an even number, and therefore I can go 12 times 2, 24 oxygens here, and another 6 there. So that's a total of 30. And so I need a 15 to keep it balanced. So, one above it, just to repeat, 8 divided by 2 would be 4, no problem. I can leave the 1 there, which means I would need a 3 here. 4 for my hydrogens, 8, 4 times 2 is 8. And then finally, there's 6, and another 4 is 10. So 6 and 4 is 10. 10 divided by 2 is 5. And so whether I have a 1 or I have a 2 simply depends on looking at the hydrogen part. And then that's how I would balance all of the combustion reactions that we may get. In general, we are only going to have to worry about these 5 types of reactions: direct combination, decomposition, single replacement, double replacement, and combustion reactions. And so let's turn to this sheet now. And you can see our 5 types of reactions. Combustion, single replacement, double replacement, direct combination, and decomposition. Please note for the last 2 that direct combination is also called synthesis. When we synthesize something, we are creating or making something, combining things together. Decomposition can also be called analysis. When we analyze things, we try to break it down to figure out what's going on. So, let's do some more practice at types of reactions. One thing, splitting into 2 things. What type of reaction would this be? Correct. This would be decomposition. All right, next we have 2 things turned into one thing. What type of reaction would that be? Good. Direct combination. When we combine things, that is direct combination. Please note again that decomposition can be analysis, and direct combination can be synthesis. All right, the next one. Okay, I heard somebody say double. Please note, if it's going to be double replacement, it's going to be 2 compounds goes to 2 compounds. That's not a compound. That's just zinc by itself, and over here we have just hydrogen by itself. It's a diatomic, but it's still just hydrogen. So this, in fact, is single replacement. Okay, next. CO2, H2O. That's right, combustion. Okay, calcium, compound, aluminum. Single replacement. Again, notice how I'm trying to get you to keep these straight. You don't pay attention so much to what the actual compounds or elements are, you just look at their patterns. And so in this case I have element and compound, compound and element. Whereas in the next one, notice compound, 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 and therefore double replacement. In 7 here, I have in fact broken into 1, 2, 3 things, but it's still 1 being turned into others, decomposition. Compound, 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 compound. 2 compounds to 2 compounds. Double replacement. Compound and compound combined into another compound. Okay, even though these are compounds and not individual elements, I'm still combining things. And so just like number 2, this is still going to be direct combination. The key is 2 things got turned into 1 thing. And then the last one here, number 10, again, CO2, H2O, that is a combustion reaction. So, little practice with the 5 types of reactions. All right, let's do some more balancing to practice with. Again, look for things that are different. 3 chlorines here, 2 chlorines there, make the switch, 2 and 3. Now I have 6 chlorines on both sides. 2 times 3 gives me 6 over here. 3 times 2 gives me 6 over there. And of course, when I put a 2 there, I need a 2 here so that the aluminums are the same on both sides. Okay, number 2. Now, both the nitrogen and the titaniums are different. However, I do note that whatever I have for my nitrogens, this one here has got to be twice that in order to match the 2 and the 4. So I could just as well start with the titaniums. I notice 3 here, 1 there. So let's start off that way. And of course, if I have a 1, I still have 4 nitrogens. So I need 2 there. Now please note, I could have any multiple of these 3 numbers and that would still work. So in other words, a 4, a 6, and a 2 would still work. But we want to, as we would with fractions, reduce them down to the smallest whole number ratios that we can use. All right, next one. One SO4, one SO4. An H2, an H2. A zinc and a zinc. They all match. Well, since they all match already, it is okay to have all ones when everything is already matching. Okay, here's one of my combustion reactions with the hydrogen. Notice 6 cut in half is 3. I'd want to put a 3 there to make it 6 hydrogens over here, but I cannot have an odd number there. So I'm going to start off with the 2, which means that has to be 12, so that I have 2 times 6, 12 carbons here, 12 carbons there, which means a 6 here, so that the hydrogens are also, in this case, going to be 12. And then, similar to one we just did a few moments ago on that other paper, we have to have a 15 here. Five. Again, the chlorines are different. Always start with one that's different. So I would put a 2 here and a 3 there. So now my chlorines match. But of course, since I put a 3 here for the calciums, I'm going to need a 3 there. And with a 2 here for the aluminums, I'm going to need a 2 there. All right. So as part of your homework, you will finish the rest of these and then go on to the other handouts and work on those as well. More practice with balancing, more practice with types of equations, and also a little bit of practice with the formulas, where you will be given the formula name and then you have to figure out what ions, for instance, that would include. Make sure you balance your charges correctly in producing the compound, and then once you have the equation written out, you can balance that chemical equation.